All right, let's talk about one of the most important ideas in all of software development, object-oriented programming, or OOP for short. It's kind of like the invisible framework behind so many of the apps you use every single day. So today, we're going to pull back the curtain and see what makes it tick.
So here's a wild thought for you. Most of the software we use today is built on a core concept that's, well, it's from the 1960s. I know, it sounds a little crazy, but it's true. To really get our heads around why this one idea has had such incredible staying power, we first have to understand the huge problem it was created to solve. So before OOP entered the scene, programming had a massive problem with, well, rigidity. Just imagine you're trying to renovate a house, but moving a single wall could make the whole roof cave in. Seriously, that's kind of what software development was like back then. Making even one tiny change was a huge risk and could break everything in totally unpredictable ways.
Yeah, early code was basically a long, straight line of instructions. Think of it like a row of dominoes. Sure, it's simple to set up, but if you nudge just one domino in the middle, the whole thing comes crashing down. It was just incredibly fragile. OOP completely flipped this idea on its head. Instead of one long line of instructions, it said, hey, let's focus on the things we're working with. This let developers create these self-contained modular blocks of code that you could rearrange and reuse safely, kind of like Lego bricks, a total game changer.
The real genius of this new way of thinking comes from a simple but brilliant analogy that helps organize everything. And that analogy is the blueprint. Okay, so the first key term you absolutely have to know is a class. Now, a class isn't the thing itself. Think of it as the architect's blueprint for a house. It lays out all the rules. It has to have doors, windows, a roof, but it isn't an actual house you can walk into. It's the master plan, the design on paper. And that naturally leads us to the object. If the class is the blueprint, the object is the real deal physical house that gets built from that blueprint. You can't live in the drawing, right? You live in the house. So the object is a real, tangible instance that was created based on the rules of the class. And this is where it all just clicks. The true power of OOP really starts to shine. Because from that one single blueprint, our class, we can build an entire neighborhood of different houses, or objects. Each one can have its own unique flair, maybe a different paint color, or different people living inside. But they all share that same fundamental structure defined by that one original plan. So what's actually inside one of these blueprints? What makes them work? Well, let's pop the hood and take a look. A class is really made up of three main parts that define what it is and what it can do.
First up, we've got fields. The best way to think about these is like the internal wiring of the house. It's the raw data, it's absolutely essential, but it's hidden away behind the walls for a reason. Next, you have properties. A property is like the thermostat on the wall. It gives you safe, controlled access to that internal data. I mean, you don't go rip open the wall and rewire the furnace just to change the temperature, right? No, you just turn the dial. That's a property. And finally, we have methods. This is the fun part. These are the actions the object can do, like open the door or turn on the lights. They're the verbs that bring the object to life.
Now, these blueprints aren't just thrown together randomly. They're built on a set of really powerful architectural principles. We call them the 4 pillars of OOP, and they're what make this whole system so incredibly strong and reliable.
Okay, let's do a quick flyby of these pillars. First is encapsulation. That's just the idea of bundling all the data, the wiring, and the methods, the light switches, together into one neat package, the house. Next is information hiding, which is just common sense, really. It means putting up walls so people can't just mess with the internal wiring directly. They have to use the thermostat. Then there's inheritance, which is all about reusing your work, like using a basic house blueprint to create a bigger mansion blueprint. And finally, polymorphism. This one sounds tricky, but it just means different kinds of houses can respond to the same command in their own way. Now, those last two, inheritance and polymorphism, that's where things get really, really interesting. So let's zoom in on them.
All right, let's tackle inheritance. To make this clear, let's switch from houses to boats for a minute. Imagine we create a very basic blueprint, a base class called boat. It just defines the stuff that all boats have in common, like, say, a length. Now, here's the cool part. We can create new, more specific blueprints, like one for a powerboat and one for a sailboat, that inherit from our original boat class. This means they automatically get all the features of a standard boat, but then we can add unique stuff to them, like how many engines a powerboat has, or how many sails a sailboat has. It's called an is-a relationship. Every powerboat is a boat. This is huge because it saves us from writing the same code over and over and over again. And that brings us to the real magic trick, polymorphism. It's a fancy word that literally just means many forms. And it's this idea that you can use the exact same command and get completely different results depending on the object. For example, we can treat both a powerboat and a sailboat as just a generic boat. But if we tell each one to move, they do it differently, right? One fires up its engine, the other raises its sails. Same command, totally unique behavior. That is the power of polymorphism. Now, these pillars, this isn't just a bunch of abstract theory. This stuff is the absolute bedrock for the powerful tools that developers use every single day to build the complex applications we all depend on. Okay, so you've designed your boat blueprints and you've built a whole fleet of objects. Now what? How do you keep track of them all? Well, that's where collections come in. Just think of a collection, like a list, as being a harbor. It's a handy, flexible container that can hold all of your different boat objects, and it can grow or shrink as boats come and go. And once your harbor is full of all these different boats, you need an easy way to find what you're looking for. That's where modern query tools come in. They give you a simple, almost plain English way to ask questions about everything in your harbor. You can ask things like, hey, show me all the sailboats that are longer than 40 feet. Or can you count how many powerboats have 2 engines? These tools let you search, sort, and filter all your objects with clean, super readable commands. So when you boil it all down, object-oriented programming is so much more than just a set of rules for writing code. It's a way of thinking. It's about looking at the messy, complex real world, with all its different objects, behaviors, and relationships, and modeling it in a way that code can actually understand. It turns chaos into elegant, organized, and manageable solutions. So really, the only question left is, what real-world problem are you going to model next?